All right. Hi, everyone. Welcome to this session. Let me find where we are. Yes, so the crypto session of FOCS. So the first talk will be Extractors and Secret Sharing Against Bounded Collusion Protocols by Eshan Chattopadhyay, Jesse Goodman, Vipul Goyal, Ashutosh Komar, Shin Lee, Raghu Meka, and David Zuckerman. All right, please go ahead.
Hi everyone, I'm Ashutosh, and today I'll be talking about a joint work with Ishan, Jesse, Vipul, Shin, Raghu, and David. So let me begin by defining bounded collusion protocols, which we recently defined in a joint work with Meka and Sahai. So basically a P-party BCP allows any set of P parties to collude in each round and write a bit on public code. So let's try to understand the model using an example of P equals to 2. So in this model, say in the first round, the first pair colludes and writes a bit on the board. Now based on the bit written on the board, adaptively any other pair can collude. Say the second pair colludes and writes this bit. So this process continues on. And this is a very natural communication model to study because it generalizes the models that have been studied in literature. So in case there is no collusion, when P is equals to 1, this has been studied in the name of number in hand protocols. At the very other extreme is number on forehead protocols, which are very fascinating, as in there are n parties sitting in a circle, and there's a number written on forehead of each party. So any party can't see his own forehead, but he can see n-1 other foreheads. So when he is speaking, it is as if the n-1 parties are colluding and speaking. So n-1 party and BCP is exactly equals to n party NOF. But now we have a parameter P. This allows us to interpolate this entire rich spectrum. So in this work, we'll be focusing on 3 different facets of BCP. First, we'll be looking at communication complexity. Then we'll be delving into the world of pseudo-randomness through extractors. And finally, we'll be looking at cryptography in the context of secret sharing. So there will be context switching, but to give our results, we have to do this. So let's begin. We can define P-party communication complexity as the minimum amount of P-party BCP communication required to compute the given function f. So why do we study communication complexity lower bounds? Because it allows us to prove lower bounds in like streaming algorithm lower bounds and circuit lower bounds. In fact, to prove super logarithmic lower bounds for NOF model is one of the most outstanding problems of complexity theory because it implies circuit lower bounds. So a natural question to study is, can we get a lower bound for the entire spectrum of BCP? And indeed, our first result is precisely such a bound. So if the formula is too much, let's look at the most interesting setting of parameters. So for any number of parties, even if we allow like 99% parties to collude in each round, we can achieve a polynomial lower bound against BCP communication. So to contrast it with the situation in number on forehead, in number on forehead, even for a very small number of parties, we do not know super logarithmic NOF lower bounds. So while BCP model allows the number of parties to be higher, the prior work could only tolerate collusion of up to logarithm. So now let's jump into our second object of extractors. So extractors, here the goal is to purify impure sources of randomness into uniform ones. So say there are n sources, x1 to xn. They are not uniform to begin with, but they have some min entropy, each of them. And now all of them are independent. So the extractor requirement says that the output of extractor when given sample from these n sources should look uniform. Again, these are fundamental objects with many applications in computer science and mathematics. The focus of our work is that can we extract even if there is some leakage on the shares, on the input sources. This was formalized as cylinder intersection extractors in KMS. So basically, it's the strengthening of the same setup. There are n sources. The extractor output should look uniform, even given the transcript of a BCP protocol running on these n sources. So what are the parameters that we would like to improve on? We would like to reduce the min entropy of each of these sources to as low as possible. And we would like to handle as high collusion as possible. So these objects were also recently called as leakage resilient extractors against BCPs. So let me get to our second main result, which we reconstruct extractors like this for two different parameter regimes. So for the case of BCP leakage, where like 99% of the parties, the sources are colluding in each round, our extractor is quite good in terms of min entropy, and we only need each of the sources to have polylogarithmic min entropy. At the very other extreme, you want to push the collusion to as high as possible, like a number on forward leakage. Say there are 5 sources and there 4 sources are leaking in each round. Then the min entropy requirement that we need is like 0.3 m. It's a linear. So just to say that the communication complexity lower bounds that have been studied in literature and actually do imply such extractors, but the entropy requirement is as close to the full entropy as possible. And each of these two results in our theorem have already found applications in cryptography and complexity theory. So let me jump to the last setting of secret sharing, which is again in our world of crypto, which basically there's a secret that needs to be shared to n parties, such that any t out of n can recover the secret. But what is required is no t-1 parties learn any information about the secret. So again, these are fundamental with applications all over crypto. The guarantee that we are interested is on leakage resilience, as in the adversary can learn some information about all the shares. So this can be modeled in multiple ways. We look at the strongest model of leakage, which is leakage resilience against BCP. So the setup is the same. Any T party can reconstruct, but secrecy requirement can be strengthened, as in even given a transcript of a communication protocol, BCP protocol, and any T-1 shares, the secret should be statistically hidden. So now notice that you can't allow T parties to collude, because as soon as T parties collude, they get the secret. So T-1 is the best you can hope for, and this was the motivation behind introducing the BCP communication model. So in our current paper, we can get P up to T by log T. So comparing it to prior work, the prior work could only get up to P up to like log T when T was very, very close to N. So now let me give the intuition behind our BCP lower bound. As in, the main idea is we'll try to reduce the communication on N parties to a communication on smaller number of parties, for which we already know lower bounds. So let's run with an example of 4 parties in which 3 parties are colluding. Say first round, these 3 collude, next round, these 3 collude. So first thing is I fix some of the inputs. So I'll be left with 2 parties. This first triple of communication can be simulated using S1 alone. The next triple of communication can be simulated using S4 alone. Now notice on the right side, we have a number in hand protocol. There is no collusion and we know good lower bounds. So what it implies is we need a lot of communication on the left side. While this already gives us something, it doesn't get us too far, because as soon as we like allow another triple to collude, there is no pair left to run this kind of simulation. So the main idea here is to, rather than reducing to NIH, we'll be reducing to NOF. So now, same example, just fix S2. I'll be left with 3 parties. And now this first triple can be simulated as a pair on the right. This triple can be simulated as a pair on the right. And this triple can be simulated as a pair on the right. And this is exactly a NOF protocol. And we know a good lower bound on the NOF protocol. So we get a good lower bound on the left side also. So let's just take a step back and see as to what we did. We found a small subset of Q parties not jointly colluding in any round. As soon as we did, we can fix everything else. And we have a NOF protocol on Q parties. Now we can use lower bounds on NOF to actually get our first theorem. So Podolsky and Serstov actually reduced NOF to NOF and can be seen as a very special case. So they obtained logarithmic lower bounds. So I like to end with open problems. So our extractors, while they are very good for BCP leakage, for NOF leakage, they require linear mean entropy. Can we go below that? Our secret sharing schemes can handle collusion T by log T. Can we actually get 0.99 T, as for the case of N equals to N? And similarly, can we find new applications for BCP? Thank you. Questions?
Thank you. If anybody has any questions, feel free to jump in. Yeah, there's a question in the chat. Do you want to read it out or should I read it? You can talk, I think.
I can check. Okay. Let me see. Just
Yeah.
1 second.
Okay, so the question is, can you mention the application of this that you referred to earlier? That's
So
the question
application
from
of
the
the
chat.
result of extractors? Yes.
I'm not sure. I'm reading a question from the chat, but maybe
Yeah.
the application
So
of
there's
BCP
a
or of
paper.
extractors?
Yeah. There's a paper on explicit extremal designs. So that has applications to a kind of extractors, like paper by Chattopadhyay and Goodman. They show how to get classical extractors and result in classical settings using this kind of BCP extractors. So that is one of the applications. And there's a paper in crypto this year by Lee et al., which actually gets leakage resilient key agreement. They are also based on NOF extractors. So these are the two applications.
Any other questions? We have about 3 minutes. So I know you said it's an open problem, but do you have any intuitions or conjectures about what type of things other applications of BCP could be used for? BCP leakage?
So this overlap might actually prove useful in like designing MPC protocols. So there might be possibility that people can compute something jointly and leak. So this is of course a conjecture that even if to get weaker forms of leakage in MPC, we might actually crucially rely on BCP leakage, stronger leakage, and use that in giving the protocol. So that is one of the possible directions. And there are applications in extractors. So these are the two things that I think are actually like this key agreement is a very nice application of this NOF. There are two parties, and there is leakage happening on the randomness of each of these two parties. Now they want to agree on a random key. So adversary is learning randomness from the first party, randomness from the second party, and he's seeing all the communication. So this is a completely classical model. There is no collusion, but it turns out that the NOF extractors and these BCP kind of ideas actually give us this kind of agreement, leakage resilient agreement.
Any other questions? Maybe one more last question? No? Okay, so thank you.
Thank you, everyone.
Who is the next speaker? You want to share your screen, see if it works?
Yeah, I'm the next speaker, and yeah, let me share my screen.
Okay.
Just 1 second.
Yeah, anyway, we're 1 minute early, so take your time. Okay, good. So the next talk is on one-way functions and Kolmogorov complexity by Yanyi Liu and Raphael Pass. Go ahead.
Thank you for introducing me. And today I will talk about my work on one-way functions and Kolmogorov complexity. This is a joint work with Professor Raphael Pass at Cornell Tech. So I'm going to be very broad to summarize the history of cryptography in the last 2,000 years. So people have invented many encryption schemes, which is amazing. However, the story of each scheme begins with an artist who invents the scheme. And for the scheme to be useful, it has to be secure against all the known attacks. And the scheme will be deployed. However, sooner or later, this scheme will be broken by someone, and we are waiting for the next scheme. So it seems that we have been going around in this cycle for a really long time, and people can never prove that the scheme is secure. So in 1976, Diffie and Helmer proposed the genius notion of one-way functions, which gives us a way out of the cycle and brings us into the age of enlightenment. So the function f is one way if it is easy to compute, but hard to invert. So it is easy to go from the input x to f of x, but it's hard to go from f of x back to the input x. And a famous example of one-way function candidate is based on the hardness of factoring problems, where we use the input x to pick two large random primes p and q, and we output p times q. So to invert this function, we have to factor this large number, which is assumed to be hard. So the good news is that one-way functions is both necessary and sufficient for a bunch of private key crypto primitives, such as private key encryptions, pseudorandom generators, digital signatures, authentication schemes, and so on. Although PKE, multi-body computation, and obfuscation are not included, whether one-way function exists is the most important problem in cryptography. So a simple observation is that the existence of one-way function implies NP is not equal to P. And to say why it is the case, for any polynomial time computable function, we can define the problem of inverting the function as an NP search problem. And if NP is easy, then any search problem can be solved in polynomial time, so which is a contradiction. So it seems that proving the existence of one-way function unconditionally is a very hard question. So our holy grail, proposed by Diffie and Helmer also in '76, is to show that NP is not equal to P implies the existence of one-way functions. However, it's still a very hard problem, and there are a lot of partial black box separations between the worst case hardness of NP and the existence of one-way function. So in the absence of the holy grail, people have proposed many candidates of one-way functions based on different computational assumptions, such as the hardness of factoring problem, the hardness of discrete logarithm problem, and the hardness of lattice problems more recently. Furthermore, people also believe that the encryption schemes used in practical, such as DES, SHA, and AES, are also secure. So far, they have not been broken. But the question is, for how long? So cryptographers seldom sleep well, said Mikali in '88. And we know that if we have quantum computers, then factoring problem and discrete logarithm problem are actually easy and can be solved by quantum algorithms in polynomial time. So have we really escaped from the dark age crypto cycle where people keep proposing new schemes? And the central question is, does there exist some natural average case hard problem that characterize the existence of one-way functions? And our main theorem says, yes, one-way functions exist if and only if T-time bounded cohomology capacity is mildly hard on average. So let us introduce the notion of cohomology capacity. And so consider the following two strings. The first one is 1, 2, 3, 1, 2, 3, and so on. And the second one is 1, 7, 3, and something, something. So the question is, which of the two strings is more random? And the notion of cohomology capacity is used to measure the amount of randomness in a fixed string. So that's k of x denotes the length of the shortest program that outputs the string x. And more formally, we fix a universal Turing machine U, and we are looking for the length of the shortest program pi, which consists of a Turing machine M and a input tape W, such that the universal Turing machine U, when simulated on M and W, will output the string X. And the notion of cohomology capacity has a lot of amazing applications, such as proving Gödel's incompleted theorem, but unfortunately, it is uncomputable. So instead, we consider the notion of time-bounded cohomology capacity. So let's k subscript t of x denote the length of the shortest program that outputs x within time t of the length of x. So with the running time bound, of course, kt of x is computable. So the question is whether kt can be efficiently computed when t is a polynomial. So this question has also been started in the Soviet Union since the 60s, and also independently by Hadmanis, Sipser, and co. in the 80s. And it is closely related to the minimal circuit size problem. And let us introduce the notion of average case hardness of Kg. And in fact, this problem has also been studied in the Soviet Union in the 60s, and they called it a frequential version of computing Kt. And the question is whether there exists an algorithm that computes Kt of x for a large fraction of x. And a simple observation also made in the 60s is that KT can be approximated within an additive factor of log n with probability 1 minus 1 over n. And the approximation algorithm is very simple, where we just output n, and n is the length of the input strings. So the correctness of this simple approximation follows from the fact that there are a lot of strings that are incompressible and thus have high KT complexity. So we say KT is mildly hard on average if there exists a polynomial P such that no polynomial time heuristic H can compute KT with probability 1 minus 1 over P of n over random string X for infinitely many n. And we define KT is mildly hard on average to C approximate in the same way, and C is basically the additive factor. So our main theorem says the following are equivalent. First, one-way functions exist, and second, KT is mildly hard on average, and third, KT is mildly hard on average to C log n approximate. And we have the following two simple corollaries. First, one-way functions exist if and only if KT is mildly hard on average. So this is the first natural average case hard problem that characterizes the feasibility of most basic tasks in crypto. And the second corollary says KT is mildly hard on average to C log n approximate if and only if KT is mildly hard on average. And we obtain a result on the hardness of computing KT all the way through the one-way function and cryptography. So let me briefly mention how our proof works. So we start from KT is mildly hard on average, and then we show the existence of one-way function, and this is just a direct construction. And then start from the existence of one-way function, we construct a object called entropy preserving PRG. And it's a new notion, and the classic construction of pseudorandom generator does not satisfy the entropy preserving property. And here we need the entropy preserving property. We need the entropy preserving property. And from entropy preserving PRG, we show that KT is mildly hard on average to C log n approximate. And if we start from 3, then 2 is basically trivial. So that's basically how our proof works. And let us end this talk by summarizing our progress towards the Holy Grail. So we start with the assumption that NP is hard for BPP, and by Ilango, Loft, Olivier 20, where they show multi-MCSP is NP hard, we know that multi-MCSP is hard for BPP also. And we know that multi-MCSP is closely related to a cohomology complexity. So if we assume cohomology complexity is worst case hard to approximate for BPP, then by Hirahara 18, where he shows if KT is worst case hard to approximate, then KT is errorless hard on average. So we conclude that KT is errorless hard on average. However, our results do not extend to errorless hard on average. And if we assume KT is mildly hard on average, then by what we have seen today, we show that one-way functions exist. So these red dashed arrows are missing implications. And we can see that it's hard to say why multi-MCSP is so different from KT complexity, and why errorless hard on average is so different from mildly hard on average. So we believe that we are getting closer to the Holy Grail. And thank you for your listening, and questions are welcome.
Thank you. Benny, you want to ask a question?
Yes, so it seems that this equivalence gives you a new way to prove the existence of universal one-way function, right? Because you know that if there is a one-way function, then you have a concrete one, right? This is the famous result of Levin. So I wonder, in Levin's theorem, one of the annoying things is that the constant, like the complexity of this one-way function is crazy, right? It depends on some crazy constant, depends on Turing machines. So can you bypass this thing by using this approach, or maybe not?
So by complexity, you mean the running time of the one-way function?
Yes, it depends on the description, right? I mean,
I would say like our one-way function construction is very efficient and it's like almost linear. So the running time of our one-way function depends on this polynomial t, where like any polynomial that is like slightly it's like 1 plus epsilon n, for example, is 1.1 n, will be good. So we can say that our one-way function construction runs in time 1.1 n. So it's very efficient.
Right. Okay. So I wonder. I mean, I think that you should look. There's a paper of Luca Trevisan that shows that something inherent in the existence of universal one-way function. So it seems that you bypass this limitation, and I don't know. It's interesting to understand where this is coming from, I guess.
And continuing. Continuing Benny's question. So if all the dotted red arrow go through, what is the constant of like the one-way function? What is the candidate one-way function you're going to get? What is running time? Is there like, can you say something about this one-way function?
Yeah, the candidate one-way function is so simple. It's just you sample a string. So like you have an input of length n, and you look at the first log n bits, and you say like you interpret the first log n bits as a number, and you truncate the rest of the strings to a prefix, and we interpret the prefix as a Turing machine, and we just run the machine for t of n steps, where t of t is basically like any polynomial larger than 1.1 n. So, but one thing to mention is that this is only a weak one-way function. So to get a strong one-way function, we have to use the hardness amplification lemma by Yao to amplify it.
And what would be the parameter of the weak one-way function? Like how much amplification will it need?
Roughly, we have to so the weak one-way function, the running time is basically 1.1 n, and the inversion probability is 1 minus 1 over p of n for some polynomial p. And
which
so
polynomial p? Sorry for
yeah, so it depends on like the hardness of this KT problem. So we say KT is mildly hard on average if there exists a polynomial p that such that no heuristic can compute KT with probability 1 minus 1 over p of n. So
what's the conjecture? What's a reasonable conjecture on this p? I mean, I'm just trying to continue the line of questioning to get to the bottom line.
I see what you mean. So in some sense, like yeah, what we could only say like if so we start from the assumption that there exists a polynomial p such that KT is, let's say, is like this hard, and we get something. We get a weak one-way function with a inversion probability depends on this polynomial.
Yanni, what I think Yuval was asking was, can you hear me?
Yes.
I think what Yuval was asking was what is the reasonable parameter for the Kolmogorov complexity problem? So the hardness, maybe 1 over n square is reasonable, right? It's reasonable question, but nobody can do better than 1 minus 1 over n square. Of course, there's order 1 over n square, and the constant is not clear, right?
It sounded like Darth Vader to me.
Yeah. So I'm not sure if it's me or it's you as well. It was hard to hear you, Rafael. you want to just repeat the constant, but then we are also out of time, so we can continue.
Yeah, I think Rafael was saying that P of n was n equals n squared looks reasonable, right?
Yeah, 1 over n squared is reasonable, but maybe it would be better to actually say 1 over order n square and
right. So basically, it's a small polynomial, maybe if you amplify, right? That's the bottom line.
But the constant there, if you could, there's always going to be a constant.
Yeah. Also, in Levin's construction, it's pretty good up to the constant, but never mind.
Rafael, the authors of the next paper will be upset that you're taking time from them.
Not for next one. I'm taking for last paper.
Yeah. That's fine. The last ones are not here. Okay, thank you very much. I'm sure there will be more discussion afterwards. I also had a question which I'll ask you offline. Okay, so let's get ready for the next talk. You want to stop sharing? So who's giving the talk? Mutu? So Mutu can share. Okay, so the next talk is it easier to prove statements that are guaranteed to be true, by Rafael Paz and Muthu Venkita Subramaniam, and Muthu is giving the talk.
Thanks, Tal, for telling my whole name. This is joint work with Rafael Paz. Thanks for tuning in. Is it easier to prove theorems that are guaranteed to be true? Well, arguably, the biggest open problem in computer science is P versus NP. But this might not be the biggest problem that we want to solve, because even if P was not equal to NP, it might be easy in practice. It could very well be the case that with high probability on all efficiently sampleable instances, NP could be easy. And maybe in the real world, these are the kind of problems we encounter. To think about this, I mean, Gurvich and Impagliazzo, thought about this challenger and solver game. In fact, Impagliazzo called this as a game between Professor Grauss and Frederick Gauss, where Grauss, from a language L, picks samples an instance X according to some efficiently sampleable distribution D, and Gauss needs to say whether it's in the language or not, and if it is in the language, produce a witness. Now, the average case hardness of this language actually can be captured via the success probability of Gauss in this game. However, there is like one thorn in this game, which is that if X is not in L, then this is not something that is efficiently verifiable. So the main question that we are asking in this work is, does this game become any easier if the instances that we solved were promised to be true? Now, this is not a new thing. I mean, very early on, Ivan and Jacobi and Ivan, Selman and Jacobi thought about these questions. They asked for hardness of instances that are promised to be true. They were motivated by cryptography, like public key encryption, where you want security to hold only for validly generated ciphertext, and in fact motivated them to introduce the notion of promise problems. So the main question we are asking here is, does the average case hardness of NP imply the average case hardness of NP problems that are promised to be true? So in the challenger solver game, does it become any easier if we were guaranteed that the instances were true? And what we answer in this work is, in fact, yes, meaning that if NP is hard on the average, then so is the class of problems where the instances are guaranteed to be true. So let me just quickly talk a little bit about the definition of average case hardness. This was formulated in the classical works of Knuth and Levin. Here I'm giving a slight variant, but they are essentially semantically the same as the original definitions. So the decision version here says that a language is hard on the average if no attacker can decide the instances with probability better than 2/3 given some efficient sampler D. The search version, on the other hand, requires that no attacker find a witness with probability at least 1/3. But in the search version, there's an additional restriction that the distribution needs to produce instances in the language with sufficient probability. Now, the third version that we are talking about in this work is the promise true search variant, where you want to say still the attacker cannot find a witness with sufficient probability, but we restrict the distributions to always produce instances in the language. So in the promise true NP search problems, I want to highlight two specific, natural subclasses of problems in this complexity class. The first is to restrict to NP problems where every instance is guaranteed to be true. This is a well-known complexity class known as total function NP or TFNP that was introduced by Megiddo and Papadimitriou. A second class is where the distributions are required to sample instances together with a witness. And this can be shown to be equivalent to a fundamental concept in cryptography, one-way functions that you heard a lot about in the previous talk. So before I get into a little bit about our result, I want to tell a little bit more about these two classes. So TFNP, these are search problems where every instance has a witness. An alternative formulation is a search problem in NP co-NP. We've known, at least recently as well, which is that hardness in this class can be implied through cryptographic hardness. Like existence of collision rest and hash functions or one-way permutation implies hardness in TFNP. Although we don't know how to show such an implication based on one-way functions. TFNP, of course, is an interesting class, important class. It includes local search, Nash equilibrium, and several other important problems. I want to say a related open problem to our motivating question here is, does average case hardness of NP imply average case hardness of TFNP? Now, there is evidence for and against. We have black box separations, partial black box separations to rule out such an implication. And more recently, by Hubacek, Naur, and Yogev, such an implication can be established under some strong de-randomization assumptions. The second class of problems, which captured one-way functions, well, this was, we heard a lot about it in the last talk. I'm not going to motivate about one-way functions, except to say that a related open problem over here is, does our average case hardness of NP imply the existence of one-way functions? This is also related to sort of the open question that was discussed in the previous talk. It was more about worst case, but here we're asking if average case hardness of NP imply existence of one-way functions. And of course, it's also central to the cryptography. And here too, we have evidence for and against. We have black box separations that rule out such implications. And we also know that such implications can be proved, assuming, for example, zero knowledge for NP, like the work of Ostrowski and Wigderson, or indistinguishability obfuscation by the work of Komorogotsky et al. More recently. So in this talk, I also want to talk about these two related open problems. Does average case hardness of NP imply average case hardness of TFNP or the existence of a one-way function? And I want to point out the obvious here that answering any one of these questions, answers are motivating questions as they are subclasses of promise true NP search. And the answer we say is yes to at least one of these questions. So what we prove is at least one of these two implications must hold. And a different perspective of our result is that in Impagliazzo's world, specifically Pesiland, where NP is hard on the average, but one-way functions do not exist, TFNP is hard on the average. And now I'm going to go a little bit into the techniques into proving our result. A key notion that we introduce here is an interactive puzzle. We use this to capture like standard notions of average case complexity and also help us to analyze these kind of results. So let me quickly define what is an interactive puzzle. Well, here is a pictorial representation. You think of it as an interaction between a challenger and an attacker, where in each round, it's an interactive process where in each round, the challenger produces random coins, followed by the attacker giving a response. And finally, the challenger applies some polynomial time function on the transcript to accept or reject. The two conditions that you want for interactive puzzles, first is non-triviality, which says that an unbounded attacker, there exists an unbounded attacker that can convince the challenger with at least 2/3 probability. And the hardness requirement is that there is no attacker, no probabilistic polynomial time attacker that can convince the challenger with probability better than 1/3. Now, this is similar to, I mean, you can think of this as, you know, an interactive argument for an empty language. So let me give you a quick, just the proof overview. I won't be able to go into the techniques, but let me tell you that first what we do is we show equivalence of this notion of interactive puzzles to average case hardness. Using classical results in average case complexity, you can show that if NP is hard on the average, NP is hard on the average is equivalent to the existence of two-round puzzles. You know, you have to go through, you know, the theorems of Impagliazzo, Levin, Trevisan, and so forth, like using classical results, but this is something that we can establish. And, you know, along this way, we can also show that if our two-round puzzle has perfect completeness, meaning that the unbounded attacker can convince the challenger with probability 1, then you get an average case hardness for TFNP. And this is straightforward. You know, you just look at the puzzle, the first message becomes the instance, and the second, the response is the witness. So this is just some basic, implications we get from our notion of interactive puzzles. But the key lemma that we show is a round collapse theorem for interactive puzzles. This can be viewed as an analog for Babai-Moran. I mean, the techniques in Babai-Moran round reduction does not work, but you know, in principle, this is what we show. We show that if one-way functions don't exist, then a k-round puzzle can be made into a k-minus round puzzle. In other words, if I have a constant round puzzle, I can make it a two-round puzzle. And this reduction, we also show preserves perfect completeness, meaning if we start with a perfectly complete puzzle, we get another perfectly complete puzzle. And we also extend another classical result that we know in interactive proofs to interactive puzzles, which we show that if I start with a two-round puzzle that is imperfect, I can get a three-round puzzle that is perfect. You know, we extend the ideas of the classical work of Führer et al. So let me just tell you how combining these ideas, we get our main theorem, and that is going to be my last slide. So we want to show that if one-way functions don't exist, then starting from average case hardness of NP, I can get average case hardness in TFNP. So here is a problem. So what we show is that as I mentioned before, if NP is hard on the average, there exists a two-round puzzle. This is possibly with imperfect completeness. Now, applying the Führer et al. Extension, we can show that there is a three-round puzzle with perfect completeness. Now, from a three-round puzzle with perfect completeness, we can get a two-round puzzle where we apply the main lemma of round reduction to get a two-round puzzle with perfect completeness. And this, we show, implies average case hardness of TFNP. And the second reduction holds only if one-way functions don't exist. So the main theorem that we show over here is, you know, if NP is hard on the average, then either TFNP is hard on the average or there exists one-way functions. At least the answer to one of these open problems is yes. Thank you.
Thank you, Muthu. We have time for maybe one question. Anyone? Okay, if I say two questions, will there be one?
I can answer at least one of them.
With a yes.
But
good.
you don't know which of them.
Yes.
What's the next step? What is a natural open question here?
Which one is true, Yuval? Which one the answer is yes to? But yeah, Muthu, what's a reasonable next step?
The answer too, no?
So, you know, we are looking, like, one of the things that doesn't get resolved here is, like, can we prove something for universal arguments, right? If I have universal arguments for some language, does it imply some cryptographic primitive or some average case hardness? This is something that we are looking into, and I would say is a natural question. And there is some work in this line, but I'm saying that this is kind of the general question.
Okay, thanks.
Okay, so maybe the next speaker will set up.
So I just need Muthu, can you stop sharing?
Iftach, you're talking? Okay,
right.
So the next talk is the tight lower bound on adaptively secure full information coin flip by Iftach Heitner and Jonathan Karidi-Heller. And Iftach is giving the talk. Sorry, I forgot to clap for Muthu. Thank you, Muthu.
Okay, so hello everyone. No, what happened to my video? It stopped.
We can see.
No, not me. Okay, so hello everyone. I'm going to speak about a tight low bound on adaptively secure coin flip. This is a joint work with my student, Jonathan Karidi-Heller, that unfortunately could not give this talk, but he is given the 30-minute version of this talk. So I'd encourage you to listen to the longer version. Okay, so almost everyone here is a cryptographer, so you know what coin flipping is. So let's just rush through it. So, it's a protocol that allows a set of parties to decide on a common Unifrom-Bit. Assume Alice, Bob, and Charlie like to go to a movie, but, so want to flip a coin, they're at home using Zoom, so they cannot just, flip a real coin. So they use a protocol. Everyone, flip his own private coin and send some messages, and eventually decide on the coin. So this is coin flipping protocol, and the question we should ask, what happens if some of the parties are corrupted? What happens if they are trying to bias the protocol, say that we're always going to a comedy movie? Okay, so this is a coin flipping protocol. This was firstly defined by Blum, by Manuel Blum in '82. He says that coin flipping protocol is a protocol such that honest party output common close to Unifrom-Bit, even when adversary corrupting some of the parties attempt biasing it. And yet many variants, different in communication model, adversarial power, etc. We are going to focus on the full information version they're going to define soon. But first, let's try to convince you why coin flipping protocol is such a fundamental task. So the obvious answer that it's important because it can be used to create common keys or public randomness. Okay, this is the obvious answer that we all know. But actually, there's a second reason, which is related to stability of random processes. More accurately, attack on coin flipping can allow us to prove impossibility results for stability of random processes. And let me give an example by poisoning attacks on machine learning algorithms. Okay, here's a story. There's a learner engine that gets as input DNA samples, and he tries to find out whether it come out from, I don't know, giraffe community or rabbits community. And the question one might ask is, if an adversary is controlling some of the samples, can he make the learner always output a giraffe? Okay, clearly can do that if he controls all the samples, but what if he only controls some of them? So this question is clearly important. It's called adversarial machine learning, but how is it related to coin flipping? So let me try to convince you. So first, as we all know, learner engine is not really engine. It's just an algorithm. It's a fancy name, but still an algorithm. And the sample is just strings, and the output is just bits, right? So now if you label the inputs and you call the output a coin, then it's just the picture I drew on the second slide, right? It's just a coin flipping algorithm. And indeed, this is what Majul, Lifar, and Mahmoudi did. They used a coin flipping attack, particularly the one that Kalai et al. They're going to mention soon, to mount a poisoning attack on machine learning algorithm. Okay, so hopefully I somewhat convinced you the importance of coin flipping protocol. So let's be more formal. So we consider full information coin flip, defined by Ben-Or and Lineal back in '85. In this model, the communication is over a broadcast channel. The output bit is the deterministic function of a transcript, and the adversary is computationally unbounded. This is arguably the simplest variant of coin flipping protocol. Okay, you have to understand nothing about crypto to figure out what such protocol is. And so this is a protocol. What is a good protocol? So we say good protocol is resilient to what a protocol is T-resilient if its common output cannot be fully biased by an adversary controlling T-corrupted parties. Okay. And now we have to distinguish whether we consider static adversaries or adaptive adversaries. So a static adversary selects the party to corrupt before the execution begins. And the study of static adversary of full information conflict closely related actually started the study of Boolean function in computer science. And there are many, many results about such attacks. In particular, it was shown that there exists an n-party protocol that is resilient to almost to constant fraction corruption. Okay, say n/2 corruption, static corruption still cannot fully determine the output of the protocol. Second type of adversary, the one we consider in this paper, is what's called adaptive adversary. This adversary is stronger. It can select the parties to corrupt during the protocol execution. After it sees some of the messages, then it can decide which message to corrupt. Do you hear me well? Because I see that the picture freezes here and then.
I hear you well. I hear you well.
Great. Okay, so what is the upper bound? So there's only one upper bound, the protocol, which is the stupidest upper bound, the majority protocol. Every party flips a bit and sends it over, broadcast it, and we take the majority. And Ben-Or and Lineal, back in the original paper, proved that it is resilient to square root of n adaptive attacks. Okay, and we even conjecture this is optimal, that any protocol can be fully biased by square root of n parties. So what about matching lower bound? So the first law, proving this conjecture. So the first one to prove, so this conjecture was proved for a very specific class of protocol. In particular, Lichtenstein, Lineal, and Sachs prove it for single bit, single turn protocol. Namely, any such protocol can be fully biased by square root of n corrupted adaptive corruption, where this protocol means that every party sends a single bit, and each party only speaks once. Later, Goldwasser, Kala, and Park prove it for symmetric singleton protocol, where symmetric means that the function that determines the output is oblivious to the name of the parties. And more recently, Kalai, Komorowski, and Raz fully closed the case of single-turn protocol. So that we proved that any single-turn protocol can be fully biased by a square root of n corruption. But the many-turn protocol was fully open. There was not even slight low bound. So we basically answer these questions. Basically, we fully answer the conjecture of Ben-Or and Lineal, show that no protocol is resilient to square root of n adaptive corruption. Or in other words, majority is optimal. The one turn, one bit, most stupid protocol is the best protocol against adaptive corruption. And more formally, we prove that for any protocol, there exists a bit and a square root of n adaptive corruption adversary that bias the protocol output to B, which save but little of 1 probability. So this proved the conjecture up to polyalgorithmic factors. And it's efficient for some protocol. It's improvement even the single turn, the one turn attack of Kala et al. Is inherently inefficient because it's recursive. Our attack is non-recursive. So it's in some setting it is efficient. And finally, the one signet is inherent. The fact that you can only bias to one direction because there exists an n-party protocol that is resilient to omega of n adaptive corruption against one direction. Okay, so this is the result. How much time do I have, Tal?
You have 6 minutes, but that includes time for questions. If you use it up, there will be no time for questions.
Okay, so let's use some of them. Okay, so I have no time to speak about the proof, of course, but let's see just one, I don't know, one philosophical thought about of how to attack interactive protocols, okay? So the bottom line is to attack them gently. Let me explain what do I mean by that. So to attack gently mean that even under the attacked execution is close to the unattacked, to the uniform unattacked executions. For instance, assume that attack managed to do that the attack's execution is the uniform one, condition that the common output is 1. So it's a very successful attack, but on the other hand, like with probability 1/2, the common output of a coin flipping protocol is anyhow 1. So it's really even saying Kale divergence is very close to the uniform execution. And why is it important? So for several reasons. First, property of the original execution are maintained for the attack. For instance, if the original execution didn't have large change in expected outcome, then also the attacked execution. It's very handy. Second, and it's very important for many-turn protocol, for attacking many-turn protocol, attacking parties are not signal out for the attack because the execution is very close to the original one. And this is crucial because when you attack many-turn protocol, it's easy to see that a corrupted attack has to attack many times. And if after the first time it attacked, it is signal out, it's clear that it's cheating, the other party is going to ignore it. And therefore, your attack going to fail. And finally, it yields a simpler analysis. And indeed, such variant of GELNA attacks we use in Arden simplification proofs and many variants of coin flipping results. So let me just conclude. So we proved that majority protocol is optimal coin flipping against adaptive corruption. In a work in progress, we consider stronger version of adversary, which is called strongly adaptive, which can decide whether you'd like to corrupt a party after seeing its message. And if it's corrupted, it can withdraw the message. And for such adversary, our attack is two-directional. We can attack the protocol both to 1 and to 0. It is more efficient in some setting than the current attack. And that's all. That's maybe one quick open question. So our attack is success with safe but a little of 1 probability. Can you push it to negligible probability? And second, so our attack works, you apply square root of n attacks and we bias the protocol, but it doesn't give, if you just allow to corrupt t times, it doesn't give t times square root of n bias. So can you come up with an attack that after attacking t times, you get t square root of n bias? And thank you.
Thank you, Iftach. So we do have like 3 minutes, 2 or 3 minutes for questions. If anybody has a question to Iftach.
Iftach, is the log cubed kind of inherent to the attack, or is it your analysis? And are you hopeful of improving that?
Good question. You know, it's like 10 p.m. in Israel, so the log cube is a bit hard for me to recall where is it coming from. No, I don't think it's inherent to attack. It's more inherent to the way you analyze it. Okay, you analyze K divergence and sum up to be able to push the calculation through. We need to, you know, like to chop some tails. So I'm not clear it's inherent to the attack.
K divergence.
Mm-hmm.
The main tool you're using is just analysis by KL.
Yeah, when I said that the actual distribution is close, the corrupt attack distribution is close to the uniform distribution, we use K divergence. You know, in some of the calculation, we just being it crude to make it go through. So I'm not sure the log cube is essential.
Thanks.
Okay, are there any other questions? If not, thank you, Iftach. Yeah, Yuval, you can ask.
Yeah, any relation whatsoever between whatever, you know, questions still exist in this space in the full information model and questions about coin tossing in the cryptographic model? Any technical overlap?
So, you know, I'm working very hard, someone to say too hard to diminish these questions, you know. So, I don't know. I don't know. I'd be happy to hear more. I mean, I guess maybe taking the approach of Mahmoudi et al. To use coin flipping approach for poisoning attacks on adversarial and machine learning is very important. I mean, like to make this attack efficient, because like there's many settings that if you can make this attack real efficient, I don't know a lot about the importance of adaptive corruption on adversarial machine learning, but if someone do care about it, then there are important open questions to handle. In coin flipping per se, I mean, my bucket is empty. I don't know. Maybe Tal is one. I don't know.
Okay, thanks. That's pretty convincing.
Thank you, Iftach. So you want to stop sharing so the next speaker sets up? Thank you, Iftach. Okay, let me see. Okay, so the next talk is the round complexity of perfect MPC with active security and optimal resiliency. by Benny Applebaum and Eliran Kachlon and Arpita Patra. Okay, Eliran is giving the talk, I guess.
Yeah, thank you.
Go ahead.
So hi everyone, my name is Eliran, and in this talk I'll present a joint work with Benny and Arpita about the round complexity of perfect MPC with active security and optimal resiliency. Let's start with the model. We have n parties that communicate over secure point-to-point channels, and they also have access to a broadcast channel. And the parties want to compute a joint function f of their private inputs. And perfect security essentially means that the computation is error-free, even in the presence of a computationally unbounded adversary that corrupts up to T parties, like in this example. And by error-free, we mean that the honest parties always get a valid output, and that there is a zero probability of cheating by the adversary. And in particular, the adversary learns nothing from the computation other than the output of the functionality f. Now, there are two kinds of adversaries. There is a passive adversary that always follows the protocol, but tries to learn information about the honest party's inputs. And there is an active adversary, which is allowed to deviate from the protocol. And in this work, we focus on the most challenging case of an active adversary that corrupts up to a third of the parties, which is the best that one can hope for in these settings. So those are the settings, and let me just mention some features of perfect MPC. The first one is the unconditional security. There is no need in hardness assumptions, and security works even in the presence of an unbounded adversary. The second one is the simplicity of the definitions and the analysis, and the perfect MPC also has strong composability properties. And in many cases, tools and ideas from information theoretic cryptography are used in computational cryptography. So after presenting perfect MPC, we should ask, is it even possible? And this question was answered by two papers by BGW and CCD in '88. And they show that every function f can be perfectly computed in the presence of a passive adversary when there is an honest majority, and in the presence of an active adversary when there is a strong honest majority, which means that the adversary corrupts less than a third of the parties. And in both cases, the bounds on T are optimal, and the complexity is polynomial in the circuit size of the functionality f. And for the round complexity, it is in both cases it is linear in the multiplicative depth of the functionality f, which is the maximum number of multiplication gates from the output node to each of the input nodes. And this is, of course, related to the degree of the function f. And as I've said, in this work, we are interested in the round complexity of perfect MPC in the presence of an active adversary that corrupts up to a third of the parties. Okay, so there is a large body of work on the perfect MPC, and I will not be able to introduce everything. I do want to mention the work of Isha and Kushilevitz that show that every function can be perfectly computed in a constant number of rounds. And their work is based on the randomizing polynomials paradigm, in which they show that every function securely reduces to a degree 3 computation. And by applying the BGW on a degree 3 computation, we obtain a constant round protocol. Now, more recently, there was a breakthrough in the round complexity of perfect MPC. So for the passive case with an honest majority, two work, one of Applebaum, Bakersky, and Sabari, and the other of Gargisha and Srinivasan, show that every function can be computed in 2 rounds, which is optimal for this regime. And another work of ABT showed that for the active adversary with suboptimal resiliency of t less than n/4, every function can be computed in 3 rounds, which is again optimal for this regime. Now, the key ingredient in the work of ABT is a new paradigm, which is called multi-party randomized encoding, or MPRE, in which they show that every computation reduces to a degree 2 computation. And finally, I should mention that all the protocols in this slide are only efficient for log-space computations, but the results are still meaningful even when the protocols are inefficient because we consider unbounded adversaries. And finally, the question of what is the optimal round complexity of perfect MPC with active security and the optimal resiliency remains open. And in our work, we answer this question. So we completely characterize the round complexity of perfect MPC with optimal resiliency. And we show that every function can be perfectly computed in 4 rounds in the presence of an active adversary. And as before, our results are only efficient for OWFs-based computations. And our upper bound consists of 2 parts. The first one is an efficient 4-round protocol for degree 2 functionalities, where the computation is done over some large field. And what we essentially show is that the round complexity of degree 2 functionalities is at most the round complexity of the verifiable secret sharing functionality plus 1. And because we know that the round complexity of verifiable secret sharing is 3, then we get a 4-round protocol. And the other component is the completeness theorem. We showed that the completeness of degree 2 functionalities over a large field of characteristic 2. And before, such a result was only known to work over such a completeness theorem was only known to work over the binary field. And again, what we actually show here is that the round complexity of general MPC is equal to the round complexity of degree 2 functionalities. And taken together, these 2 results show that the round complexity of general MPC is at most the round complexity of VSS plus 1. And finally, we show matching lower bound. We show that for t equals n over 4, there exists a functionality that has no 3-round perfect protocol. Okay, and again, we show that this 1 round gap between VSS and MPC is inherent. Okay, so let me say just a few words about the lower bound. We won't have time to talk about the upper bound. So in the lower bound, our goal is to show the impossibility of a 3-round protocol when t equals to n over 4. And our starting point is the lower bound of GIKR, Rishai, Kushinevitz, and Rabin, that show that there is no 2-round perfect VSS when t equals n over 4. And note that VSS is a very simple function that has only a single output from a single party and a single input from a single party, and all outputs depend on this input. And therefore, our intuition is that a general functionality that mixes the inputs of the parties should be more expensive, should take more rounds than VSS. And one way to formalize it is to show that if we have a 3-round protocol for general MPC, then we should have a 2-round protocol for a 2-round VSS protocol. And again, by the impossibility results of JKR, this is impossible. And so we get a contradiction, and 3-round protocol for general MPC should be impossible. And this is exactly what we do. We take a 3-round, any 3-round protocol for some good functionality F. We chop the last round of the protocol, and we show that we get a 2-round VSS protocol. Okay, and therefore, what we actually show is that the round complexity of VSS, the round complexity of general MPC is at least the round complexity of VSS plus 1. Okay, and finally, the conclusion. So we showed a strong connection between MPC and VSS. As I've said, our completeness theorem shows that the round complexity of general MPC is equal to the round complexity of degree 2 functionalities. And our protocol shows that this is at most the round complexity of VSS plus 1. And our lower bound shows that this is at least the round complexity of VSS plus 1. So we can conclude that the round complexity of general MPC is equal to the round complexity of VSS plus 1, which is 4. And finally, let me just summarize the trade-offs between the resiliency threshold and the number of rounds with perfect security. So for full active security, we have a 2-round protocol when there is only 1 corrupt party. We have a 3-round protocol for the n over 4 threshold, then we have a 4-round protocol for the n over 3 threshold. And beyond that, it does not matter how many rounds we had, we cannot get any better threshold. And I also want to mention a new work in which we show that if we are willing to compromise on statistical security, then for the n over 3 threshold, every function can be computed in 3 rounds. And again, this is optimal. So, and note that this creates a strong separation between statistical security and perfect security, because it means that that all functions can be computed in 3 rounds with statistical security, but even simple functions cannot be computed in 3 rounds for perfect security. And finally, I want to mention an open question. So by the work of Rabin and Benor, we know that for statistical security, functions can be computed, every function can be computed even for the honest majority threshold. And an interesting open question is what is the exact round complexity? And that's it. Thank you.
Thank you. Are there any questions? I see there was a question that was answered in the chat, but Ron, you want to ask for the sake of those who are watching and might have had the same question?
Maybe if there are other questions first, because I got
Yeah, is there? Sure. Anybody has a question? Okay, yeah, so.
I just asked if you look at the problem outside of log space and insist on the honest guys being polynomial time, can you get a constant round protocol, or basically is anything better than BGW known?
Yes, so we don't know. That's great. It's an open problem.
Okay. And then I guess a follow-up was, how does this relate to randomized encodings? Would it imply some new randomizing, randomized coding for P or something like that? And I guess that's also open.
Yes. So the main question is with the randomizing polynomials of Isha and Kushirevitz. I mean, we're still stuck there.
If you don't insist on polynomial time computation, then some dream locally decodable codes will give you polynomial communication and constant round complexity for all functions, at least with a constant round complexity, at least with a constant number of parties.
So sorry, optimal locally decodable codes, like
you have like dream locally decodable codes that match the existing lower bounds, then it would imply but not with polynomial time computation, but with an exponential.
Like matching Katz-Trevisan on lower bound or something?
Yeah.
Okay, are there any other questions? Okay, thank you, Eliran. All right, so the last talk in the session, both authors could not make it. They're both in Singapore, and it's 4:30 a.m. But they sent a video, and they will also be available. There's a poster session tonight, like every night, corresponding to each session. There'll be, it's, I guess, on East Coast time, it's midnight to 1:30 a.m.
Everyone on this session has to show up. I heard that nobody shows up to the poster session, so everyone who's here, tough luck, you have to show up tomorrow. I'll tell them. More
but the authors will be there to answer questions, but we will watch their talk now and not take any questions afterwards. Okay. Good. So could you share their screen? Not the screen. Can you share the video? It worked for a second and then it stopped.
Hello and welcome to my talk. It's going to be on concentrate on malleable codes in a split state model. This is joint work with Divesh Agarwal. We are both from National University of Singapore. Okay, let's start with the brief introduction to non-malleable codes. So it's a notion defined by Dziembowski, Pietrzak, and Weeks in 2010. The idea is as follows. We've got a message. The message gets encoded. There's a code word now. And then comes evil adversary and tampers with the code word. We get some code word prime. And as a result, we get a message prime. Now, the question is how message and message prime are related. And the security requires that either message prime is equal to the message, or if that's not going to happen, then we expect that message prime is completely unrelated to the message. In other words, either adversary preserved the message or he overwrote the code word and destroyed the message. In particular, the following example should not be possible. So changing original message into message plus one, that should not be possible. So any partial information about the message should not be possible to preserve. First of all, notice that the adversary has to have limited power. In particular, he can't do the following. He can't decode, add one, and re-encode again, because that results in the message being message plus one, which should not be possible. what are the common limitations of adversary? Well, there's quite a few classes. This is not the exhaustive list. The first one was independent bit tampering. This is from the original paper. In independent bit tampering, the adversary is deciding whether to keep, flip, set to 0 or set to 1 each bit of the code word. So, he does it independently for the bits. He doesn't see the bit 1 when tampering bit 2, for example. The another class is bounded depth circuits. That's, well, we have the code word and adversary is applying some bounded depth circuit to tamper with it. Bounded locality, that's adversary is applying some function with bounded input or bounded output or both localities bounded. Bounded degree polynomial, that's self-explanatory, and one of the most popular classes is split state, if not the most popular. What's split state? Well, we've got a code word, we cut it in half. That gives us left state and right state. Now, adversary will tamper each state independently. What it means is that when adversary is tampering with the left state, he does not see the right state, and the right adversary does not see the left state. The adversaries agreed on the strategy. They share some common randomness, all that stuff. It's just when the tampering happens, I just tamper left state without seeing right state, and then I tamper right state without seeing left state. And combined left prime and right prime gives me new code word prime. Why do we care about split state? That's a good question. Well, first of all, as we discussed earlier, we have to limit the adversary somehow. And split state is very wide and natural class for which things are still possible. There's no limit on the computational complexity of tampering on each state. It's arbitrary tampering. It's just the only requirement is that the tampering happens independently on the states. So this is very natural and very strong class. It immediately gives 2 out of 2 non-malleable secret sharing, and it has a lot of applications as a tool for building other things. So first of all, it can be used to build non-malleable codes in other models and other interesting classes. In particular, the first 3 papers, small depth circuits, local tampering, and decision tree adversaries. In all those 3 papers, the idea is to use the split state as a building block. Also, continuous non-malleable codes use split state as a building block. What are the other applications? Well, we can use them in non-malleable secret sharing. The ADNOPRL blah blah uses it as a building block. There are connections with privacy amplifications. There are connections with non-malleable commitments. Okay, now let's introduce non-malleable reduction. That's a notion by Agarwal, Dodi, Skazana, and me. Once again, a brief restatement of the non-malleable code. Also, we got the adversary from some class F, and we can restate the security notion in the following way. So message prime is some function of message, and that function should be trivial. So either identity that corresponds to preserving the message, or a constant function that corresponds to completely deleting the message. Well, we can easily think about generalization of this notion, and that's exactly non-malleable reduction. So instead of requiring that G is in a trivial class, we require that G is from some family G. This is a reduction from F to G. We denote it with the arrow. G does not have to be a subclass of F. Obviously, we would like to have some non-trivial reductions, so G should be somewhat easier to handle than F. Okay, so what are the properties of non-malleable reductions? So first of all, there are strict generalizations of non-malleable codes. The non-malleable code against family F can be viewed as a reduction from F to NM, where NM is the trivial family. So it's a family containing identity and the constant functions. Moreover, reductions compose. So if I have reduction from F to G and from G to H, then by composing the encodings, I get the reduction from F to H. If both reductions are constant rate, then the composition is also constant rate. Okay, so what did we show in ADKO 15? We showed two things. First of all, we showed the reduction from split state to look-ahead and forgetful tampering. What's split state? That I already explained. So we got two states, each of them is tampered separately. Then what's to look ahead? We've got two states, each of them will be tampered separately, but moreover, each state has multiple memory peer parts, and each part is tampered in a look-ahead fashion. So first part is tampered first, then we tamper with second part while knowing the first part, then we tamper with third part by knowing the second part and first part, and so on. Right, this all while preserving the split state property. And what's forgetful, the other option apart from to look ahead, the adversary can do is, what the adversary can do is forget one of the memory parts. So one small memory part is lost, and then adversary gets to do whatever he wants. So there is no look ahead structure anymore, no split state structure. He gets all the remaining memory parts and he can do whatever he wants. In the same paper, we also showed the reduction from to look ahead and forgetful to non-malleable, which together gave which together with the previous reduction gives a non-malleable code against split state tampering, everything in a constant rate. Sadly, Xin found a bug in the proof, and the second part of the paper is only true, well, only goes through assuming the correctness of that lemma. We don't know how to prove it, and we tried quite a lot. So that leaves the big gap in that paper. So what's our contribution? Well, we fill that gap. So we give a new bootstrapping technique that allows us to get a constant rate construction of an MC against to look ahead and forgetful. That together combined with the first part of the paper gives us the non-malleable code against split state tampering with constant rate and negligible error. One has to mention at this point that Xin already got the NMC against constant rate, but only in a constant error regime. And that's not sufficient for cryptographic applications. We need negligible error. But yeah, that's it for this talk. Thank you.
All right. So I'll clap. I guess you're all welcome to ask questions to the speakers at the rump session tonight.